Welcome back, class, and we will move on uh, to chapter 5 material on amplifiers. Chapter 5 is MOS. We already did BJTs, chapter 6. So the order is reversed. You must excuse me for that. But chapter 5, MOS amplifiers, MOSFET amplifiers, we follow the same sequence. Uh, Topic 6, 7, and 8. In 6, we look at the three amplifier configurations for the MOS, similar to what we saw for BJTs. We have three terminals, so the three are grounded or made common, and so you get three different configurations. Then we look at biasing a little more, and then finally in discrete circuit applications, that means not ICs, not integrated circuits, but if you created amplifiers using just the MOSFET devices separately, discrete devices, then these are the principles you'd follow for design. Okay. All right, so that was introduction to chapter 5, and we can really go through chapter 5 somewhat quickly because a lot of the material you'll see will feel familiar because we studied the same ideas with relationship to BJTs. All right, so 5.6, section 5.6, the three amplifier configurations talks about the common source amplifier, which is like the common emitter in the BJT, then the common source with a source resistance, which is similar to a BJT with an emitter resistance. Then we have the common gate, which is similar to the CB or common base in the BJT, and finally the common drain, which is like the common collector, right? The common drain is also called source follower. And then we have a section on summary and comparisons. All right, so you can see the three configurations. First one, common source, which is like common emitter. So the source is grounded. The input, the signal, is between the base, between the gate and the source, right? For the common gate, the gate is grounded and the input is between the source and the gate. The output is between the drain and the source. Sorry, I'm going to keep getting confused. The output is between the drain and the gate, right? So here, gate to source and then drain to source. Here it's between base to here the signal is between the source and the gate. Again, the output is between the drain and the gate, and that's the common gate. Lastly, the common drain. So the drain is common, is grounded, and you have the input again applied between the gate and the drain, and the output is coming out between the source and the drain. Okay, so these are the three basic configurations, and remember the drawings are only showing you signals. They're not showing you the biasing arrangements. Okay, you must remember that the biasing arrangements with the VDD and the other resistors, they still exist, but here we are only talking about what happens with the input signal and the output signal. Okay, all right, I'm going to move on to the next slide. By the way, what happened to slide numbers? Yeah, so we looked at slide 47. Now we are on slide 48. I can magnify this. Now this diagram you'll recognize because we already saw this when we were studying BJTs, right? Characterizing amplifiers. Like we discussed there, amplifiers have three properties, important properties: input resistance, voltage gains, and output resistance, right? Actually, these have to go here, and this has to come here. Okay. So similar to what we saw in BJTs, we define the input resistance, variety of gains. There is the open circuit voltage gain without load impedance. There is the open circuit voltage gain with a load impedance. This is the formula. Then there is the uh, voltage gain VO to V signal, which is the overall voltage gain, and it can also be written in this form, right? In terms of the this voltage gain. So this is called the overall. I at least call it the overall. That means V output with respect to V signal. This is only V output with respect to the VI, which is at this point, not V signal. Okay, so that's the difference. And the output resistance, which is the, if you put a current source and you measure the voltage across it, the output resistance is the voltage measured divided by the current. So these concepts are not new, you're familiar with them. So let's move on to the actual amplifier configurations. So here also it says common source amplifier fed with signal V signal from a generator with a resistance of R signal. The bias circuit is omitted. Again, all these drawings, many of these drawings, if you don't see a VDD, it doesn't mean it doesn't exist. It just means that we are ignoring the biasing aspect of it and we are only focusing on the signal aspect of it. Okay? That's why you see grounds everywhere, right? That just means common point, right? It's not necessarily DC ground, it's just signal ground. Here you see the same common source amplifier as shown here, but the transistor itself is replaced by the hybrid pi model. And one big difference you'll notice is that the gate is shown with an open, right? You know that. Gate carries no current in a MOSFET, and hence an open circuit is what is shown in the model. Okay. And then we have the transconductance GM multiplied by the input voltage. This results in current, right? Then you also have the RO, which is the output resistance. Sometimes the output resistance is neglected, but it depends on the early effect. Sometimes it's included. And then you have the drain resistor, which is also shown in this circuit. And you'll also have a load resistor sometimes. So you'll have not only the output resistance is the parallel combination of RD and small RO, but it may also have load resistance. So there may be three resistances in parallel that give you the output in some problems. Okay. Without the load, of course, you call it the open circuit, gain. Okay. If you added unbypassed resistance in the source lead, right? So in this lead, previously in this lead, there's no resistance. Now if you add a source resistance in this lead, in the source lead obviously, then you modify that to a CS amplifier with a source resistance. And as we have seen before, there's a lot of benefits to doing it. And we'll talk a little more about it, but you already know the benefits. Similar to the BJT case, the benefits are that you get a higher input impedance using this. More importantly, for variations of beta, or in this case, variations of Vt, in MOSFET case, the amplifier can still be designed so that the device variations don't destroy the performance of the amplifier. Okay, the analysis of the amplifier can still be done properly, even if the device properties itself vary quite a lot. Okay, so so let me add one more thing. Uh, there is a source resistance. Sometimes the source resistance is split into two parts. You'll have one part of the source resistance not bypassed, but the other part of it can be bypassed with a capacitor. So what that does is, only for signal frequencies, that extra portion is a short circuit, right? Because the capacitor conducts during with signal frequencies, and so it becomes a short circuit. But for biasing design, you can consider the whole of the resistance value, both the unbypassed and the bypassed, for bias design. Okay, so that's one way. Sometimes the RS is split into two portions. Okay, all right. So whenever you have a resistance in the source circuit, we adopt the T model for small signal analysis, right? So instead of this model where you use the GM VGS combination to come up with the value of this dependent source, here we use just a I, and the resistance here is replaced with a 1 by Gm. Gm, is a conductance, so if you flip it, you get a resistance. So that resistance is used in the model. Okay, and the T model is more useful when you have this extra resistance. So that's the rule. Okay. Otherwise, everything else you can see is pretty much as defined. So there is a V input, right? This is after this resistance. So this V input is what gets magnified. And then GS is the drop between the gate and the source. Okay. Um, and then looking from this side, you have RO is basically RD, right? RO equals RD. And this is the output across the drain. If you connect a load here, then obviously the same VO applies to the load also, but the effective resistance here becomes a parallel combination of RD and RL. Okay, so that's what you should remember about the CS amplifier with a source resistance. So here are a few more points about the common source amplifier with a source resistance. RS can be adjusted to control the magnitude of the signal VGS and ensure that VGS does not become too large and cause high nonlinear distortion. So regardless of how large V signal is, you can drop a lot of it and make this VGS, which is also the input to the amplifier, this VGS can be reduced by tuning the value of RS. So we'll do some problems on understanding how to adjust RS so that you don't have too large a value that can then cause the device to go into outside of saturation. Remember, saturation in MOSFET means like the active area, right, where the actual amplification happens. So you don't want to go into the triode region or the cutoff region by having too large of a signal. So the RS helps to limit that. So only a fraction of Vi appears between gate and source as VGS, right? Whatever is Vi, only a part of that appears here, and that's what gets amplified. So VGS equals Vi into this factor, which is always less than 1, and you can write it as this. So including the resistance Rs reduces the voltage gain by this factor 1 plus Gm by Rs. Okay, it reduces the gain factor. Okay. Next, we come to the common gate amplifier, which is similar to the common base amplifier that we studied for the BJTs, right? So, what are the characteristics of a CG amplifier, common gate? It has a low input resistance, small gain, GV, the overall voltage gain is small. It has excellent high frequency response. So again, the use of this is more like a buffer. Nobody says, I'm going to design an amplifier and get great amplification like 40 or 50 times amplification using a CG. No, you use a CS for the main amplification. But the CG and also the CD, those are for impedance matching or buffering applications. Okay, remember that. Alright, so to do the analysis on a CG, according to our textbook, you should use the T model, right, instead of the hybrid pi model. So in the T model, you can see that a current source has appeared. Also, the input resistance is 1 by Gm. The input voltage is shown at this point at the source, right, because the input here is applied to the source, not to the gate, and then the output is still picked off across the gate resistance drain resistance RD. The output resistance RO equals RD, and the voltage output comes out of here. This I is to be calculated, okay, and we have formulas for those. Okay, finally we have the common drain amplifier or source follower. This is similar to the emitter follower in the BJT case. The source follower has a very high input resistance, a relatively low output resistance, and an open circuit voltage gain that is near unity. That means almost 1. Voltage at the source terminal. So that source terminal is where the output comes out, right? So the input, now the drain is grounded, the input is applied to the gate with respect to the grounded drain, and the output is picked off at the source terminal with respect to the grounded drain. Okay, so I hope that's clear. So because the gain is unity, there is no change in the output voltage compared to the input voltage in open circuit conditions. Okay, and so the open circuit gate voltage gain is near unity. Voltage at the source terminal will follow that at the gate input, hence the name source follower. Okay, all right, let's see what else is said here. Common drain amplifier or source follower, equivalent circuit of the source follower, which is B, obtained by replacing the MOSFET with its T model, right? You put the T model here. Note that RO appears in parallel with RL, and in discrete circuits, RO is much greater than RL. Neglecting RO, we obtain the simplified circuit. So here we have taken out RO because it's very high compared to RL is what is being said. So you can ignore it, and so you are left with the rest of it as follows. This looks a bit easier to understand, right? Alright. Now this 0 again is 0 current is the property of a MOSFET because no current flows into the gate terminal. Alright. So there's a nice summary here of the various formulas. Just as I showed the table for the BJTs, there is a summary for the MOSFETs also. So before we look at this, I kind of copied these formulas also because you will use this GM and this RO quite a bit in here. So how do we get GM? This is, you can do this if all this is given, or the simpler version of the formula for GM is 2 times ID divided by V over voltage. Okay. Then output resistance RO, which we tend to ignore quite a bit, but nevertheless if you need it, then it's VA by ID or this 1 by lambda ID. Both these formulas are okay. And VA is that early voltage divided by the drain current. Now for PMOS, the same formulas can be applied, except you must use the absolute value of the VOV. Sometimes VOV can be negative, but you must ignore the negative sign and use only the magnitude for VOV, for VA, for lambda, and also instead of mu n here, right, which is some kind of conductivity, remember, for n-type semiconductor, you have to replace that with its mobility, I think, yeah. You have to replace that with mu p in this formula, okay. So that gives you GM and RO. Now once you know GM and RO, you can start looking at these values, these formulas for the input resistance, open circuit voltage gain, output resistance. Then this is open circuit voltage gain, but with a load resistance attached. This is overall voltage gain, which is output voltage across the load divided by the input voltage, which is the V signal actually. Okay, so these are your formulas. So these formulas, in my opinion, are simpler than for BJTs, right? Because the input resistance is infinity, right? Now this column is not infinity, not like an open in for BJTs, and that's why the Rn keeps coming everywhere. But here, luckily, because it's infinity, at least in these three cases, only for the common gate you have some value here. The formulas make it a little bit easier. Similarly, output resistance is just RD, right? RD, 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 and then for the source follower it becomes 1 by GM. Now remember, for the source follower, the unity gain amplifier, AV0 is 1. Okay. Once you have a resistor in the load, then the output resistance has to be modified. The drain resistance has to be modified by including the parallel RL, right? So all these formulas now become this. And this can also be written as this, is what this is trying to show you. So these are two different methods, two different formulas, same result, but they are written differently, and sometimes one is better than the other. Similarly, here also there was another formula that I got somewhere. I put that in here too. Okay. All right. Here Rn is 1 by Gm, so you can put the 1 by Gm here. I guess. Oh, this gain equals this gain. Sometimes you'll run into this issue in source follower circuits. So the gain from uh, the output voltage across the load to the input voltage is the same as the overall gain, which is the gain of the output voltage divided by the V signal, right? So these two tend to be similar. Okay, the MOSFET output resistance RO has been neglected in these calculations, as is permitted in the discrete circuit amplifiers studied in these chapters. For IC amplifiers, which we'll study later, RO cannot be neglected for MOSFET transistors, so they must all be taken into account, and some of these formulas will get modified to include the RO. Okay. All right. Let me skip ahead. So here's a summary, a quick summary of all the comparisons between these 3 or 4 configurations of amplifiers. Now, I do advise you to read the textbook. There's a lot of material on the, first of all, how are these formulas being derived? You can look at that. Secondly, there's lots of insight and information about the various properties of these different amplifiers and where they are used for. There's some specific examples that make it easier for you to understand. So all that is in the textbook material. I can't read obviously the whole chapter. It's more than 80 pages of material. You're going to have to read much of it yourself. But hopefully I've at least given you a good introduction, so as you start reading, you'll understand better. Let me at least walk you through the summary of these and comparisons of the 3 different types of amplifiers. So the common source configuration is the best suited for realizing the bulk of the gain required in an amplifier. So you may have one CS stage, or you may have many CS stages called cascaded stages. So the output of all these, the total gain is the product of all the individual gains, right? So if you have one stage of amplification 50 and another stage of amplification 40, the total gain is 50 times 40. It's 200, right? 2000, right? Yeah. So to get high amplification, you will cascade, and that's what it says here. Either a single stage or a cascade of 2 or 3 stages can be used. Now, adding a resistor Rs in the source lead of the CS stage provides a number of performance improvements at the expense of gain reduction. So gain drops, but many other improvements in performance happen. Number 3, the low input resistance of the CG amplifier makes it useful only in specific applications, right? So if you have like an application where from the previous stage or from the previous device, like a microphone, you're getting a signal, but it's at a low output resistance, and you need to feed that into your CS amplifier. But the CS amplifier can only work well when its input resistance is high, right? When the signal coming in is at a high input resistance. If you cannot, so you need something in the middle to match the two impedances, and that's where the CG amplifier is useful. This also, the high frequency response is better than the CS amplifier. So that makes it useful in some applications which we may see later on. Lastly, the source follower or the common drain amplifier finds application as a voltage buffer for connecting a high resistance source to a low resistance load. So if you have a load, again I always use the example of a speaker, because speakers, as some of you may know, the resistance can be as low as 8 or 16 ohms. At least the old style speakers with a cone and all that, a moving membrane. So those kind of speakers, they have low output impedance, and to connect your CS stage to the speaker, you need a matching uh, stage in the middle, and that matching stage is generally a source follower or common drain type voltage buffer. Okay, all right. So having studied all this, we have some examples on just the basic amplifier properties, and um, some basic voltage gain and RO, R input, R output type calculations. So those, I have them, and we will come back to this in my next recording. So I have the next stage is to discuss biasing on amplifier circuits. Just as we have seen for BJTs, biasing in MOSFETs also follows similar logic. The goal is to find a proper Q point that helps us implement the amplifier without causing it to run into the non-linear portions of the input-output voltage curve. So the Q point has to help us pretend that the device is entirely linear in operation, even though we obviously we need to be in the saturation zone only. We cannot go into the triode region or the cutoff region, but within the saturation region only a certain portion of the curve is good for linearity, right? And if you don't have a linear amplifier, you're going to find distortion between the input and the output. So your pure sine wave or whatever is on the input, combination of sine waves, is going to come out quite distorted if you're not in the linear portion. So picking the Q point is important, and some techniques to pick the right Q point is what we are going to discuss here. Now another thing that makes it difficult to pick one Q point in our design and let it go is that such a Q point may work for one transistor that you picked from the store. But then you go back and you get another transistor from the same store with the same exact serial number and the part number. You'll find that its property, some of the important properties such as VT, COX for example for a MOSFET, they're not the same. So even though you thought you had one circuit that worked very well for one transistor, it's not going to work so well for another transistor of the same family. So you have to have some means to account for the variation, the manufacturing variations that naturally occur. Hence, some simple biasing circuits that we have seen in the past will not work for mass producing these amplifiers and creating electronic products. So you have to modify your biasing circuits and make them more robust. So this particular slide, slide 60, shows you, for example, if you pick two devices from the same family and you think, okay, I've got this VGS that I'm going to bias at, and that will give me a corresponding ID1 or the drain current. For another device, the drain current is almost 3 times as high at the same VGS, right? So to overcome this, we will look at some modified biasing circuits. All right. So here is one popular solution, a simple solution. You first fix VG. The gate voltage is fixed, and the only modification you do is now to bring a resistance in the source circuit, RS, right? So by having this new component, the resistor in the source circuit, You're able to overcome some of those manufacturing issues that we just talked about. And what you'll find is the action of this RS works to keep ID, the drain current, as constant as possible through something called negative feedback. And then compared to the case of a fixed VGS, the variability obtained in ID, as you'll see from this graph, is much smaller because of the presence of the RS. Okay. All right. I have on slide 62 a series of drawings, but they all refer to one type of biasing. We have seen a similar type of biasing for in the case of the BJT also. So rather than try to provide a fixed voltage at the gate and then have a separate voltage as VDD for operating the rest of the transistor, now we try to work off of one power supply, right? So using one VDD and a voltage divider network, you can then get the necessary gate voltage, the bias voltage, off of that same battery source, power source. So this is exactly like the voltage divider biasing method we saw in case of the BJT. You'll also notice that the emitter sorry, not the emitter is for the BJT, but the source resistance that we just talked about, that also appears. So basically you have three resistances that help you fix the bias point. RG1 and RG2 are in the gate circuit, RS is in the source circuit, and of course you have RD in the drain circuit, which is absolutely necessary too. So a lot of problems that we'll solve consist of finding these values for these four resistors and also calculating the drain current ID. So using one power supply VDD, you derive VG through a voltage divider, and you see these formulas for how to calculate Rin, RO and voltage gain in the case of such a voltage divider biasing network. Okay. So look at the figure. Part C says biasing using a fixed voltage at the gate. Basic arrangement. B, reduced variability in ID. C, which is what we see here, practical implementation using a single supply. D, coupling of a signal source to the gate using the coupling capacitor. So once you have derived this biasing voltage divider network, you can't just attach your signal source straight to the gate, right? You have to use a coupling capacitor so that only signal frequencies go through the capacitor. The capacitor is an open circuit for DC, so whatever biasing voltages exist, they don't come back here. Only when this capacitor behaves as almost a short circuit, zero resistance, at signal frequencies, then we do the analysis by neglecting the bias voltages and focusing only on the signal voltages. The same subsystem can also be implemented using two supplies, one at the drain VDD, which is the one we use most, but if you have a second battery, you can connect that to the source, and this makes it even more of a robust biasing system. But obviously the price you pay is that you require two different batteries or power sources. So for most applications that we'll consider in this class at least, we'll stick with the basic resistive network using one battery. Okay. So I have problems and examples in the remaining slides, which I will come back to in my next recording. Let's finish the few remaining theory slides. So here is an example of another um, biasing method where all you do is you take the one supply, the VDD, take a portion of it back and put it into the gate using what's called a negative feedback or degeneration resistor, RG in this case. Okay, so this is also a popular method for biasing. It's reasonably accurate, not as accurate as with the voltage divider network, but it's also commonly used. And these are all for discrete circuits, not if you're designing for ICs, for integrated circuits. Why? Because ICs, it's very difficult to create resistors in ICs, right? It's expensive to create resistors within an integrated circuit. It's much easier to create transistors. So if you look at the next slide, 66, you'll see exactly what I'm talking about. Instead of having a lot of resistors, here we put a constant current source in the source circuit, in the source, across the source terminal of the MOSFET. So this constant source, I, as you can see, is a constant current source, itself consists of two other FETs, Q1 and Q2. So the purpose of this Q1 and Q2 is only to create a constant current I, which you can then put into your amplifier's source circuit to help it bias it. So the cost of creating this constant current source, it's also called a constant current mirror. So this mirror circuit consisting of two transistors is cheaper actually to implement on an integrated circuit than to go find new resistors to add. Okay. Alright, so that should do it for biasing. Like I said, most of the problems I'll have the time to do with you will generally be around the resistive network biasing. So the last section, the theory section here, is 5.8, and here I try to wrap up all the concepts that we have studied so far in chapter 5. Everything from the physics of the device, our very first introduction to NMOS and PMOS, all the the characteristics, the input output characteristic we studied, then learning about biasing, all this, and then of course amplifier behavior, amplifier types. All this will come together in this section, and we'll do some actual amplifiers, design some actual amplifiers. This section is always a little hard in the sense you have to try different things to make it work. It depends on your knowledge and your creativity. So we look at some solved examples and some exercises, and hopefully that will help you understand better. All right, again the basic structure, if you're going to stick with this biasing, R in is RG1, RG2, and then VI. So the gate signal here at the gate, VGS, is VI. And what is VI? VI is V signal into Rn by Rn plus R signal, assuming there is a signal source here coming in through a coupling capacitor. So this Rn is nothing but the parallel combination, and that's how you proceed with the analysis. So here are some figures. The common source amplifier. I think you've seen all this before. There's nothing new here. The problems and exercises are what will be new when we try to solve them. Here with the source resistance, I've given a few more formulas. Please take a look. Make sure you understand these formulas and get ready to use them in solving problems. More exercises than the common gate, more formulas. source follower, some problems. I tried to bring this back to remind you what saturation triode means. This is useful to solve problems. And then we have a section that we'll ignore for the moment because we'll study more of this in chapter 9. So with this, I finished the theory portion, and in my next recording, we'll do problems on MOSFET amplifiers.